In part B, we're going to look at the SN1 reaction, which is a unimolecular reaction. In an SN1 reaction, the bond making and the bond breaking happen stepwise, or one at a time. If you recall, in the SN2 reaction, it was happening at the same time. For SN1 reactions, the bond making and bond breaking happen one at a time. The rate of the reaction depends on the concentration of the substrate only. So the S in SN1 stands for substitution, just like it did with SN2. The N also still stands for nucleophilic. The 1 stands for unimolecular. So again, the rate of the reaction depends on the concentration of the substrate only, which is why the unimolecular is there. The mechanism of the SN1 reaction involves first the leaving group leaving. So there's a loss of leaving group. So that's the arrow that you are seeing. So when that happens, we form a carbocation. And then a nucleophile comes in, which could be any generic nucleophile. This is our electrophile. And this is going to be hugging here. So this is your nucleophilic hug with the nucleophile. So in the kinetics of SN1 reactions, it is a little bit different because of the way that the reaction occurs. In this example in particular, a tertiary alkyl halide, or this tert-butyl bromide, undergoes ionization in a polar solvent. So that means that it's going to form the carbocation. So that first part of the activation energy is the loss of the leaving group. After the loss of the leaving group, we form the carbocation, and then you get the nucleophilic attack, or the nucleophilic hug. So what you see shaded in this turquoise or blue color that's the substitution part of the reaction. In this case, the nucleophile is ethanol, which also happens to be the solvent, and this is a proton transfer that happens after that. So there's an extra hump here if the proton transfer is involved. So those are 3 mechanism arrows that can occur in an SN1 reaction, and you end up with a substitution product here. So the solvent in SN1 reactions can also act as a nucleophile, which is sometimes called solvolysis. And the same steps are occurring as in an SN2 reaction, but it's in a different order and not at the same time. Because of the mode of the mechanism, the substrate trend is opposite to SN2. So in an SN2 reaction, the methyl was the most reactive and the tertiary didn't happen. But for SN1, this is the most reactive, and this is the least reactive. And we'll look at why on the next slide here. In SN1 reactions, a carbocation will form more quickly if it can stabilize itself. So if you have a tertiary carbocation, this can be supported by all of these surrounding neighbors through induction, and that's going to be more stable than a secondary carbocation, which is more stable than a primary, which is more stable than a methyl. So this is least stable, and this is most stable. So the tertiary is supported by induction. The benzylic and allylic carbocation are stabilized by resonance. So if a carbocation can form and be stabilized, then it will form more quickly. Okay, so for these practice problems, draw the carbocation intermediate that forms with each of the following SN1 substrates. So this is my leaving group. I'm just going to label all of these. This is an I here. And the first arrow for all of these is loss of the leaving group. So the electrons between the halogen and the carbon will go on to there. So that one is a tertiary carbocation. This is a benzyl carbocation, and that's on the carbon that is next to the benzene ring. So that one has resonance stabilization. This one leaves here. This is a secondary carbocation. And this one looks like secondary, but there is a carbon double bond next door. This is an allylic carbocation, which is resonance stabilized just like the benzyl one. Stereochemistry in an SN1 reaction, if you recall in the SN2, that inverted the stereochemistry. In an SN1 reaction, the carbocation leaves, so the leaving group leaves, and then it becomes planar with the carbocation. The nucleophile can then attack from either side because it doesn't have any sterics that it has to deal with. The leaving group has already left, so this frees up both sides of those. So you actually end up getting 50% inversion, which means that half of it will switch and half of it is retained. So you'll get a mixture of both because it can attack from either side. In an SN1 reaction, sometimes you need to have a proton transfer step to occur before the substitution even happens. And so why would that be necessary? Here you can see this is an OH. The OH is trying to leave, but this does not happen. OH minus is a terrible leaving group. Water is trying to leave, so water will succeed at leaving, and then we have that. So if you can protonate the alcohol via a proton transfer, that makes it an excellent leaving group. So in the mechanism of an SN1 reaction, in this particular one, if the OH is the intended leaving group, we have to do a proton transfer. So the OH picks up a proton from an acid, and then the leaving group leaves. So this is loss of leaving group, which is the water. Then we get nucleophilic attack. And this is our nucleophile. Here's our electrophile, and that's the substitution product. So one very important thing to remember about SN1 reactions is that you must have an excellent leaving group. Sometimes in SN1 reactions, a carbocation rearrangement will occur. First, the leaving group leaves, which results in a carbocation, and this may rearrange if a more stable carbocation can form. So again, the leaving group will leave because it's excellent, and the resulting carbocation can rearrange if a more stable carbocation can form. So the migrating group or atom has to be next to the carbocation, so it won't rearrange from 2 carbons away, and the rearrangement occurs only if a carbocation is formed. So this does not happen in SN2. So in this reaction we have loss of leaving group, which forms the carbocation. So if I look at the adjacent atoms, here's an H here. If I move this H over to this carbon, that H gets moved here and the carbocation is here. This one is primary, this one is secondary. This is not more stable. The carbon next to it has methyl groups. If I take this whole methyl group and shift that here, that carbocation moves here. This is tertiary, which is more stable. A mechanism for these rearrangements. So we have loss of leaving group. So if I move the hydrogen from here, that just makes a primary carbocation. I can move one of these methyl groups over to here. So that moves there. And the carbocation now is tertiary. So it was secondary. Now it is tertiary, which is more stable. So I can add water, which will act as my nucleophile. This is my electrophile. So nucleophile can attack or hug the electrophile. And everything comes along with it. So we have that positive charge there. Then we need to do a proton transfer. So let's go back and write the steps here. So that was loss of leaving group. This is a rearrangement, nucleophilic hug, and then proton transfer. All right, so this is an interesting one. These are both neopentyl bromide, so those are the same thing. And this does not happen. We do not actually get loss of the bromide here because it would otherwise form the carbocation that is primary, which is disfavored. But what happens is the methyl group can anticipate that wanting to leave and just moves over initially. And then you form that carbocation and this alcohol here. For solvent effects, in an SN1 reaction, you want a polar protic solvent that will stabilize the leaving group and the carbocation. So in polar protic solvents, the reactions occur much more quickly versus the polar aprotic solvents here. So you can see the graph here. Polar aprotic solvents have much higher energies. Polar protic is lower because it can stabilize both of them. So draw the complete mechanism and product for the above reaction, and then draw the coordinate diagram including transition states. So the mechanism-wise, first we're looking at an OH, which is a bad leaving group, so it's going to need to get protonated, and I'll grab acid to do that. All right, so that's a PT step. Next, our leaving group will leave. So ethanol is our nucleophile. Electrophile. This is our leaving group. So nucleophile is going to hug the electrophile. So everything comes along. Oxygen has positive charge. This is a nucleophilic hug. And then we just have a proton transfer. So the HSO4 minus can grab that hydrogen. And then we get that ethoxy. So the phase diagram, you get the formation of the carbocation, and then the proton transfer, and that does that.